Welcome to another of our ongoing seminars on behalf of the Theoretical Physics Group of the Australian Institute of Physics. I'd like to start by acknowledging the traditional custodians of lands all around Australia, and in relation to the Canberra region in particular, the people of the Ngunnawal Nation. We'd like to pay our respects to their leaders, past, present and emerging. The Theoretical Physics Group of the AIP is a topical group that you're most welcome to join simply by logging into your membership portal on the AIP website, and you'll see the Theoretical Physics Group name under topical groups in your membership profile section. It's free, of course, if you'd like to join, and in doing so, we will enable you to keep up to date about any significant events and future seminars and so forth that are happening in relation to theoretical physics around Australia. So far in this series of talks, we've had a range of seminars on diverse areas of current work in theoretical and important work in experimental physics that relates to theory. And if you missed those and you'd like to see them, they're all available to watch on the AIP YouTube channel, as this talk will be also in a few days. The subject of today's talk deals with the topic of strong coupling between light and matter, and in particular, how this is enhanced by embedding two-dimensional layers of semiconductor in an optical microcavity. This leads to the formation of so-called exciton-polaritons, which result from strong coupling of visible light with excitons, bound states of electrons and holes. In the case of strong coupling or ultra-strong coupling, the exciton-polaritons need to be regarded as distinct particles in a sense, in that the physics of the resulting structure often differs from that, at least qualitatively, from the physics of the exciton or the photon when considered separately. Similar thing happens in the deep strong coupling limit in other cavity QED systems, such as that which occurs in the deep strong coupling regime between electromagnetic fields and superconducting flux qubits, for example. So to talk about this really interesting topic, today's speaker is Professor Meera Parish from the School of Physics and Astronomy at Monash University. Professor Parish is an ARC Future Fellow, and she's worked on a range of topics in condensed matter physics, to cavity quantum electrodynamics, and in particular to the theory of strong correlated phenomena in electron gases and electron systems and low dimensional systems. Her talk today, which I think is going to be really interesting, is entitled Light and Matter Coupled Quantum Systems in Flatland. Thanks, Meera. Over to you.
Yeah, thanks, David. That was a very nice introduction. And thanks for the invitation to give a talk in this very nice series. So what I'm going to be talking about today is something that I've become interested in over the past few years. As David mentioned, it's the very interesting topic of light-matter interactions, particularly when they're very strong. I think just to set the scene, as we all know, light-matter interactions are pretty important. It's something that we encounter in our everyday life and crop up in all sorts of different areas of physics. And for instance, ways in which we probe a sample, by imaging the sample, for instance, relies on light-matter interactions. Or you can use light to manipulate objects. For instance, using optical tweezers, which was a Nobel Prize-winning idea. And also something that we've been thinking about in the Fleet Center of Excellence, which is what I'm part of, is can we even use light to change the electronics of a device and transform the properties of a material. So as I mentioned, what I'm interested in particular is what happens when you have very, very strong light matter coupling, and when you can start to entwine the properties of both photons, so light and matter, into one object. And so to start with, I think, so here's the outline of my talk. I'll start with just stepping back a bit and explain at least what I mean by the so-called polaritons, the hybrid light matter particles that form when you have a very strong light matter coupling, and how you can realize this. Give you a little bit of an introduction of their properties and how one usually thinks about these objects. And then I'll be turning towards a very interesting topic that's, at least what I found interesting, is what happens, if you want to look at the interactions between these polaritons, these objects. This is something that's actually been very difficult to analyze both experimentally and theoretically. And so I'm going to try and put forward a lot of, what I think are relatively simple approaches, theoretical approaches to this problem, and how you can gain quite a lot of insight from that. This is a very complicated system, but there are actually ways in which you can, general principles you can formulate about the problem. And then finally, I'll touch very briefly on what I call the very strong light metacoupling regime, which I'll come to at the end. Okay, so to begin with, what I'm interested in particular is the so-called situation where I have, the matter part is the so-called exciton. Okay, and so how you actually form such an object is if you imagine that you have like this is like represents some kind of band structure here. You have a filled band here, and then you have an empty one. And then if you excite an electron into this empty band, it leaves behind this positively charged hole. And this can now then actually form a bound state, a bound object, a so-called exciton, which is really the solid state analog of the hydrogen atom. Or you can even think of it really as a solid state analog of positronium in some sense as well, where you have the particle that's binding with its in some sense its antiparticle here. And so this is something that's it has the whole series of hydrogen bound states in 2 dimensions typically, which is what I'm going to be looking at in this case rather than 3. And it's, as you might suspect, because it's formed by exciting an electron out of a band. This is not it's not a long-lived like stable object. It will eventually recombine. This electron will eventually go back into the original band and emit, in this case, emit a light, a photon. So you have a photon that excites this electron. You can form your exciton, and then eventually it can relax back and emit the photon. Okay, so then what one typically does then is okay. So normally if it was just isolated, you'd excite your exciton and that would be it. But now if you have a situation where you confine your light between mirrors in this microcavity, this optical microcavity, like so this schematic here, what you can do now, so you can get your photon, if you can imagine it sort of bouncing back and forth, and it constantly can interact with some embedded material, in this case, some 2-dimensional layer or atomically thin material, which contains your exciton here. So you can, so what this means then is that you can constantly have a situation where your photon excites and the exciton re-emits, excites, re-emits, repeatedly, multiple times. And so you basically end up with a superposition of this photon in this cavity and this exciton. And so what you end up with now is the so-called polaritons, where you now, instead of being able to think about each of these individually, you think of it as this hybrid particle. This is a superposition of the exciton plus this photon. Okay, that's the sort of simple way of thinking out. So you have this object which has components of both light and matter. So and you can even, if you want to sort of put some maths onto it, you can. The simplest way of describing it is really like thinking of sort of a 2x2 matrix. You have your exciton, you have your photon, which can in principle have an energy difference from the exciton energy. So the exciton, imagine it's just set by the minus its binding energy here, and then you have some coupling here. This omega here, which defines the coupling between your two particles. And then when you diagonalize this matrix, you end up with your two types of polaritons here. You have basically a higher energy polariton, your upper polariton, and a lower energy one here. So if I were to sketch it now, in terms of, if I have an energy versus momentum diagram here, which I put down here, actually, so what's kind of interesting is that, you could in principle vary the detuning, vary the energy difference between the excitons and photons in a number of ways. One way, I'm putting one way here is to vary the momentum. And what you might notice, and what might at first sight seem surprising, is that here I've put down an energy versus momentum dispersion, which assumes that I have a photon with a mass. Yes, so it has a quadratic dispersion rather than normal kind of massless linear dispersion. And that's really a consequence of having confined your photon within your cavity. So in other words, so what I'm plotting here is if I'm thinking of the momentum within the plane, so you've confined it, and then I have the momentum in the plane of my semiconductor, that actually now, because of the confinement along the perpendicular direction, that actually gives rise to this mass of my photon now. So now, but I think the thing is, it's still a very small mass, a very light particle. We're talking about, you know, many orders of magnitude smaller than the exciton, and that's something that will play a key role in what follows. But you see now, basically, here's a schematic. You have a situation where you start with your two kind of particles, photons and excitons, and once you turn on the coupling, you end up with now these two different branches, this upper and lower polaritons here. There's two polaritons. Okay, so now, so that was just understanding this, essentially a single polariton. Yeah. And now you might ask, okay, so in practice, one looks at multiple polaritons, and you can realize all sorts of phenomena. You can, like there was a very kind of famous experiment from only 15, 20 years ago, where they realized Bose-Einstein condensation, where they essentially could see how these bosonic polaritons, the bosonic objects, they all condensed into the lowest energy states. In this case, they're condensed into the zero momentum state in the plane. Okay, and they also, related to that, you can see that you also have superfluid behavior, where you see that this kind of coherent state of polaritons can flow past an object here. And more recently, or most recently, there's been even interest in, you know, can we look at how the polariton actually impacts correlations between photons? Okay, and so for all of these phenomena, I mean, these are just a sample of many things that have been looked at. But these in particular, these phenomena rely on there being an interaction between polaritons. So photons by themselves don't interact, but once you make this hybrid object involving light and matter, they can interact by their matter part. And so there are interactions between polaritons, and yet surprisingly, the actual nature of them, I mean, is relatively poorly understood, like even the size of the interactions. And the various reasons for this, I mean, so if I think about it from the experimental side of things, okay, so how do I go about measuring the strength of the interactions between polaritons? So one way in which you would do it, I mean, it seems, and that's what many experiments have done, is you look at your, oops, sorry, let me just restart that. One second. All right. Okay, so as I said, there are various ways in which you can measure this. And the simplest thing is you imagine, say, you have your condensator polaritons, they're all condensed into your lowest momentum state here, your lowest energy state, as you can see here. And then you look at what happens, you know, how the energy changes when you pump more and more photons, and create more and more polaritons, create a higher density of polaritons in your microcavity. And you look at how it shifts. And so then it would seem like, oh, I just need to look at, you know, the energy shift and compare it to the density of polaritons. And then I can extract the interaction strength by just looking at this constant that relates the two. Yeah. So that seems straightforward. The issue here is actually working out what the density of polaritons is. And indeed now, if I show you here is a plot where it just shows you a bit of almost a scatter plot of showing all the various experimentally extracted values of this polariton interaction strength. So here on this axis here. Okay, and here it's plotted as a function of exciton fraction. So as I mentioned earlier, the polariton interactions are derived from their matter component. So you would expect the strength of the interactions to go up the greater the exciton fraction. So you can generally expect an overall upward trend as you increase this fraction. Okay, but what you can see actually also is that, you know, there's a huge range of measured values for this interaction strength on this plot. it's spanning several orders of magnitude. It's not like you're out by a factor of 2, you're out by potentially a factor of 10 to the 2 or 10 to the 4. So there's a lot of disagreement over what is the value from these kind of experiments. And as I mentioned, the main issue is actually working out what this density is, because there are many reasons why you can end up with an energy shift. There are a lot of so-called optically dark states hanging around that can actually also impact this energy shift. So that's one of the experimental challenges of actually trying to estimate what is, or extract what is this strength of the interactions between polaritons. The other thing is, theoretically, it's actually relatively challenging as well. So in principle, what we just need to do is we want to calculate, if we want to calculate, say at least if I'm thinking of it at low densities, the first order correction would be, what is the, I just need to look at the 2 polariton problem, like look at what are the interactions between 2 polaritons. So it seems like I just need to solve a 2 polariton problem, and I'm interested in here, how you would in principle do that is I would say, well, okay, I just take my Hamiltonian of my system, I subtract off the non-interacting part. So if I'm interested in, say, looking at the 2 polaritons at lower polaritons at k equals 0, I subtract off that part, and then the leftover part should give me my interaction strength, okay, divided by area. Okay, so 2 polaritons in a given area. Now, though, as it turns out, though, this is a bit more challenging than just solving 2 polaritons, or two particles in general, because you have have a multi-particle problem. You have electrons and holes, and you're making up your excitons. So you actually have at least a 4-particle problem. Plus, there's the photon hanging around as well. So how does one go about solving this problem? So basically, for the past 20 years, essentially the state of the art was this so-called Born approximation, where you simply take your 2 polariton wave function, this two particle state here, and you say, and you do the rather sort of, I guess, brutal approximation of just saying they just have the wave function of 2 non-interacting polaritons here. So these are basically 2 polaritons. It says momentum 0 here. Okay, so not unaffected by the interactions, and then you use that to calculate your interaction strength here. Okay, so so now what we can at least show is that while this might be a fairly kind of drastic approximation, it's actually very useful in the sense that what we realized is it's quite useful because it provides a nice upper bound on the interaction strength. So this is assuming that there are no lower energy bound states, because basically it's a simple kind of idea of the variational principle, where you say, well, if I approximate my wave function just by this, just by some approximate form like this, I know that will give me an upper bound. Assuming this is corresponding to the ground state, this will give me an upper bound on my ground state energy here. So, of course, this requires there to be no lower lying states, hence this requirement. There's no nearby lower bound state here. Okay, so these scattering polariton states are the ground state that we're interested in. So if you can go through, you can work out then from this that this interaction strength G has to be less than, well, okay, there's an exton fraction squared here, as you might expect. The exton fraction appears, and there's 2 polaritons, so hence you have the exton fraction squared. And then you have some constants times these exton parameters, the exton binding energy and the Bohr radius squared here. So actually, if you look closely, this doesn't actually even depend on a length scale. So if I multiply energy by this length scale squared, I end up with just an inverse mass. So this G doesn't even depend on a length scale. It's actually just depends on the exton fraction and the inverse mass. Okay, so this gives us an upper bound on the interaction strength. So and here, actually, what I should mention here is that what we've assumed throughout this process is that we've assumed we've had identical polaritons here. So what this this calculation gives you, it really arises from the fact that you have identical electrons and holes in your excitons that make up your polaritons. So it really relies on the fact that you have identical polaritons. So then, but then actually one thing I've sort of haven't mentioned before, but what actually you might worry about is, what about any kind of internal degrees of freedom of your polariton? And in particular, you have what I would say refer to as a spin or a pseudo spin of the polariton, because you can actually have, you can have two types of polaritons, because you can have two types of photons that in principle are in your microcavity. You can have your right circularly polarized photon, or your left circularly polarized photon with different angular momentum. So these can interact with different excitons, if you like, different spin configurations of the particles in your exciton. So here I mean, the actual spins will very much depend on the material you're interested in. Here I've just picked the configuration you would have, say, in an atomically thin material. But in principle, but basically the key point is that you have two types of polaritons based on the two types of photons you can have. And they have two different, they have +1 and -1 angular momentum. Okay, so you can also worry about what are the interactions, what are the spin dependence of these interactions. And this is also something that you can go ahead and look at within the Born approximation, and using this kind of same idea of having now two different types of polaritons. And as I mentioned, though, this result relies on there being identical particles within your exciton. So now actually, if you go through, you'll find that actually the interactions are 0 between spins. Whereas, okay, like same spins, once again, we're back to the identical polaritons. So they have this result here. The Born approximation is the original one I had here. Okay. So based on this, then, okay, so this is something that already people had known. I mean, I think our main point here, the main contribution I guess we made, was to talk about how it can actually bound the interactions. So that based on this, people originally thought that the spin up and spin down interactions, this ones, they're negligible, and the interactions between same polaritons, up or down, had this form here. Okay, and okay, now based on our analysis, though, okay, you can conclude two things from the fact that you get 0 for this up-down case. Well, either you can conclude that the interactions, this is an upper bound, so the interactions actually must be attractive for these between different polaritons, or you might worry about whether there's actually, if there's a bound state around, then all bets are off as to what's happening with the interactions between up and down. And indeed, that's something we'll look at in a moment. Okay, but as far as we know, at least in the case of these identical polaritons, there are no bound states nearby. So it's only the case where you have these distinguishable particles, you have to start worrying about this. Okay, all right, so that's at least one simple approach that we can try and squeeze out stuff from that. Now, the thing is, okay, so I mentioned it was a difficult problem, a complicated problem, but there are regimes in which you can actually reduce this, and there is a hope of actually trying to make some more concrete statements about the problem and treat it actually as a two-particle problem. And that's in the situation where the binding energy, the exciton binding energy, is much larger than the energy scale of anything else in your problem, of the polariton interactions or the light matter interactions. Okay. And so in that case, what that means then is that so the excitons are much very tightly bound compared to anything else that you're considering in your system. And so you can actually start to treat them as structureless or bosons with short range interactions. Okay, so these are neutral particles, so you can really treat them as short range interactions between your excitons. So then what that means then, if you have, certainly in the case of the exciton problem, you now have an exactly solvable problem, at least in the limit where you're looking at much lower energies compared to your exciton binding energy or the size of your exciton. Because we know how to solve, this is something one does in the context of looking at atomic collisions. I mean, there are a lot of there's a lot of machinery you can apply. Very simple approaches, scattering, or basically scattering theory, you can apply to this problem. And so here, so now we know we just need to solve a problem where we just need to solve essentially this scattering amplitude or T matrix, where the lowest order term would have been the Born approximation, and now we just need to consider an infinite series of these, which we know how to solve if we can treat the interactions as very short range, or effectively zero range interactions. Okay, now, knowing that, what you run into then is, well, the surprising thing is what happens when you have interactions between particles, or scattering between these particles like this in 2 dimensions. Because what we know, I mean, this is something that's been known for many years in quantum mechanics. It's a textbook result, essentially. What we know in that case is that the scattering or interactions between such particles actually vanish at low momentum or low collision energy in 2D. Okay, so we know that actually interactions, I mean, okay, they vanish logarithmically. Okay, so here EX is some energy scale set by the exciton binding energy, probably doesn't of all the exciton binding energy. So an energy scale set by the exciton. And so we can see that we expect at least that if I take the momentum of the excitons to be 0, then the scattering will actually go to 0 and the interaction will go to 0. Okay, so how do we reconcile this then with what's happening, say, with polaritons? Okay, because we know, I mean, as far as we can see, as far as people know, there are interactions. So how do we kind of combine this idea with what we know with polaritons? So what it turns out now, the key thing is about what the energy is that goes in here. Okay, so when you actually start looking at coupling your excitons to photons, coupling them to light, you actually change the energy at which the excitons scatter. Okay, so rather than say scattering at this, like at 0 momentum, you would be scattering at 0 energy with respect to the exciton here. Okay, so the relevant energy is that the kinetic energy of the excitons here. When you couple them to light, now you shift this energy down, by this lower polariton energy here. And it's set by the light matter coupling. And so now what you find actually, and this is something you can go and calculate, you can actually extract an interaction strength for zero momentum polaritons. That actually, so once again, you have this logarithm appearing, but now the relevant energy appearing is the polariton energy with respect to the exciton here. Okay, so you have your exciton fraction as usual, as you expect. So it still depends on how much exciton you have in your polariton, but it also depends on the energy of your lower polariton, or your energy of your polariton here. Okay, and also you have this exciton mass here. Okay, so this is for 2 identical polaritons so far. So one last thing though. So you might think I've done something dodgy here, because I've just told you that the interactions should vanish for particles scattering in 2D. And now I've just produced something where it's finite. And I mumbled something about energies and so forth. And I think the key thing here though, because you might wonder, okay, how have I solved this problem? Why have polaritons not, why do they still have a finite interaction? Why are they, what's different about them? Why haven't they got vanishing interactions? And the key really is that it's to do with the mass ratio here. So the interactions are governed by the exciton part, and they have a different mass out here, whereas the energy shift is governed by the photon plus the coupling to light part over here at 0 momentum. And so basically, if you go and work it out, you'll find that the scattering does eventually vanish if you go to low enough momentum here in your scattering. But in order to, the momentum scale you need to go to is related to the exponential of the mass ratio, or right, or rather than minus this. So this is minus 10 to the 4, basically here. So actually, if you work it out, you need to go to length scales more than the size of the universe to actually see the polariton-polariton interactions vanish. So this is really a consequence of the huge mass ratio, well, the mass ratio difference between your excitons and photons, and the fact that your interactions are governed by the excitonic part. Okay. Right. So what's kind of intriguing about this then, and counterintuitive about this, is that even though the polariton derives its interactions from the matter part, you find that actually the polariton can actually have stronger interactions, between polaritons than the original excitons. Okay, so here I've plotted. This is just the scattering. So G would correspond to this T matrix at k equals 0. So the interaction strength at k equals 0, and now I've just plotted it as a function of momentum. And if I look at the real part of that, which gives me a measure of the interaction strength, you see that the polariton interaction strength is much larger than the exciton. Well, sizable, quite a bit larger than the exciton one, like factor of 2 or 3 here. Yeah, even as I vary it as a function of momentum, and eventually they end up being the same, because at large enough momentum, I end up having, I approach an excitonic type of polariton. Well, I end up basically an exciton rather than a polariton anymore. Okay. But anyway, so what's surprising then, just from going through this argument, is that you find that polaritons can actually interact stronger than excitons. And it's really just to do with this, essentially the energy dependence of your scattering or your interactions in 2 dimensions. And the large mass ratio, I guess, as well. All right. So now, so now one last thing about this is then you might wonder what is the effect of the spin or the polarization of the light. So as I alluded to before, so when we were calculating, just trying to approximate the interactions between different distinguishable polaritons, so up and down polaritons, and we were finding that the Born approximation gave us 0 for the interaction strength. But then the question is what about the effects of nearby bound states? And in particular, you find that 2 excitons that are distinguishable, have distinguishable electrons and holes, can bind to form a biaxaton state, so an analog of a hydrogen molecule here, a hydrogen 2 molecule. So and this turns out to strongly impact the scattering or the interactions between polaritons with different spins or different polarizations. Okay. So now if you come back to here's our diagram again about this is our lower polariton diagram where it's shifted in energy from the exciton. If now I happen to have a biaxaton state that's nearby or around this point or underneath or near the polariton energy, this is actually going to dominate the scattering between the polaritons. In fact, it's going to be the relevant quantity that determines the scattering between your polaritons. And so actually what you find is that if you go back to calculating the scattering, the repeated scattering between polaritons, the relevant energy scale now that sits in your logarithm here is the biaxaton energy. Actually, the biaxaton binding energy here, I should say, so it's positive here. And what you can see automatically from this expression is that you'll end up with a divergence of this parameter, so a biaxaton resonance, whenever this binding energy of the exciton matches the twice the lower polariton energy, so it matches the energy of 2 polaritons here. So if 2 polaritons have the same energy as your biaxaton, then you end up with enhanced interactions. Okay. So this, so this is something also that people have had come up with a few years ago as well in various materials. And what's interesting though is that what you find is, generically speaking, for a range of different materials, you find that this holds that the interactions, so contrary to what you might have expected from a simple approximation involving just the lowest order term in your interaction calculation, you find that the interaction strength of up and down polaritons is actually, well, at least in magnitude, always greater than the interaction strength between identical polaritons. Okay, so so basically, okay, so we could use, in this regime, we're able to calculate these analytic expressions, and then we can go ahead and try and see whether this is at all consistent with what people have measured in experiment. And I was just going to flash quickly a couple of points here. So one is, so what people were looking at was once again the interaction shift of the polariton peaks. So you have these various polariton peaks, how they shift as you pump it harder. And okay, there's presumably, once again, as I mentioned before, there may be issues of dark states and entering into this as well. So one has to be careful with concluding too much about the actual magnitude of the interactions. There may be a lot of, it's a complicated setup, but what they could look at least is how the interaction strength varied as when they changed the polarization of their light. So this will give them access basically to, you know, what's the relative interaction strength between polaritons of, you know, up, or the same spin, or polaritons with different spin, different circular polarizations. And what they would concluded from this is actually that the interaction strength between up and down was greater than that between identical polaritons, which is consistent with what we were finding. The other thing, actually, this was another experiment in a different system, in a kind of a semiconductor quantum Weyl system, where they were confining polaritons and looking at correlations, so photon anti-bunching, so looking at how the repulsion between polaritons could lower the probability of being found together. So that's kind of what this G2 function gives a measure of. And so you can, if you work out, you know, so this minimum of this G2 function is related to the interactions of your polaritons. So basically, for no interactions, you will just have one here, but the interactions give you a sort of a dip in your, or the repulsion gives you a dip in this function here. And this was giving you a measure of essentially the total interactions, both the interactions between up and up down, because there was no kind of spin resolution. And if you extract the numbers from this, what you find is that the interactions that you get out of this actually exceed what you would expect just from the Born approximation. Okay, so basically, well, I just told you the Born approximation is an upper bound. So this is there's something obviously kind of one has to stop here and think, okay, what does that mean? Well, I guess there are a couple of possibilities. One I think, which is perhaps the most likely given the experimental setup, is that actually, once again, this G up is large. Like we've got a Biaxaton nearby, and so this is actually, once again, much larger than G up. G up down is this interspecies interaction is much larger than G up. So basically, we're back in this regime here. Another possibility is, once again, there might be some other states lying around that might contribute to this, but this seems a bit less likely, because now we're actually measuring correlations between photons rather than just an overall energy shift. So it seems less likely that other states will be, or other dark states, dark excitons or whatever, will be influencing this correlation. So what these both seem to suggest, at least, is that it's consistent with this idea that you have larger interactions between your up and down particles. And as I mentioned, when we introduce like the possibility of a Biaxaton, this actually is consistent with the interactions they measure in this experiment. Okay, sorry, so that's basically, so this is what we've at least learned from assuming that we're in a regime where the light matter coupling is strong, but not so strong that it's comparable to the exciton binding energy, sorry. So we've focused on this behavior so far, where we can actually make concrete statements. Now, what you might wonder is, what about the case of having stronger light matter coupling? So where you have a situation where the binding energy now is sort of the same order of magnitude as, or similar order of size as the Rabi coupling, the light matter coupling. So, so in that case, So that's something that can be realized, say, when you have like multiple layers in your cavity, rather than say a single layer or a single kind of atomically thin material here. So in that case, what can happen is that the light can modify the exciton wave function. You can no longer think of the exciton wave function as just being, unmodified, independent of the light. And what's interesting also is that you can at least make the case that you would expect the interaction strength to approach that of what you would expect from the Bond approximation. And the reason is relatively simple. You can argue it, at least if you look at the series that you're calculating, if you're looking at the situation where you need to go beyond the Bond approximation, you can see that if the energies start to become very large here, the higher order terms will be suppressed, and you're sort of back with the original lowest order term, which is essentially the Born approximation, so the lowest order term of your Born series here. And so this is also what's known, say, from scattering theory. If you have very large collision energies, you know what that one approaches the lowest order term in your series, the Born approximation. Okay, so if we want to actually understand what's happening here, then we require a more microscopic description, rather than just thinking of it in terms of an exciton plus a photon. If I want to be able to modify the exciton wave function with light, I need to now consider it in terms of electrons, holes, and photons. Okay. So I thought, since this is a theoretical physics seminar, I just wanted to mention just very quickly about some of the pitfalls one can come across when you write down a seemingly simple description of the problem. So what we went about doing is we wrote down, just a very simple general state for our polaritons. So we have our photon once again, and now we've explicitly written out the wave function of our exciton here, involving both the electrons and the holes here. Okay, so we have a zero momentum exciton in terms of with a wave function of electrons and holes here. And so you go ahead and once again, instead of now just having but previously we had a very simple 2x2 matrix involving excitons and photons. And now we have to have a slightly more complicated one because we're involving the wave function of our electron and hole here. So we have a kinetic part here of our electrons and holes. We have a light matter coupling term, which couples the electron hole pairs with the photons. And now we also have this I've just put in this bare cavity frequency here. Okay, so and in principle, okay, there's also you could throw in your energy for the band gap, but okay, that's not so important. So the main thing though is if you look at this, it seems simple. Okay, I just need to put it on a grid or computer and solve it. It looks straightforward to solve for the energies of this problem. Solve for the polaritons. Now, what you find actually is if you just go ahead and you just take one of this top equation and you substitute it into the second one, and you kind of rewrite it out here, and you end up with this term here, this sum over k, and then you have this kinetic part. This is this quadratic dispersion, this k squared here, and you find that this is actually logarithmically divergent in the sense that it will depend on the cutoff, logarithmically depend on the cutoff of the momentum that you have in your problem here. So you actually have sort of a hidden UV divergence in your problem that's maybe not immediately obvious here. So what do you do with this? So the temptation would be just to put in the cutoff, and that's it. But on the other hand, this kind of theory we've written down, it's very approximate. I mean, we've assumed, it's a very low energy theory. We've just written down, we've assumed this form of this light matter coupling is such that the electrons and holes, when they're close to each other, they recombine to form the photon, which makes sense. But we've ignored all the details of the lattice, of the higher bands. We haven't really included any of that. So if we want to actually have a proper theory that doesn't depend on the cutoff, it doesn't depend on high energy physics, then, the solution is well known to many other problems, is you you have to essentially renormalization. So you have to redefine the cavity photon frequency in such a way that it cancels the divergence. So you basically absorb this into your photon frequency. And so you have a new sort of energy difference or exciton photon detuning delta, which now includes this divergent part here. Okay. And there is a physical reason for why this appears, and you can basically, it corresponds to the fact that, in the way we've written it, once we've included electrons and holes, your photon can couple to very high energy unbound electron hole pairs, and this can shift the cavity photon energy. And this is actually something that's even, you even see it in experiment that you can see how, if you have a microcavity, and if you look at the photon frequency, the cavity photon frequency within the microcavity, before you add a layer of material, and then you look at it afterwards, you can see clearly that it gets shifted just by adding a layer of active material, say for active semiconductor in your microcavity. So this is a physical effect that's appearing. It's just that we just don't want it. We're not describing it in our theory, so we can absorb it and redefine our photon detuning. Okay, so that's just a kind of I thought was a kind of mathematical point, which I bring up because I was kind of surprised that this is something that's existed for a while, but no one seemed to worry about it until, we ran into this infinity when we tried to solve it ourselves. So what's nice then is that actually, so now we know how to solve this problem, we can go ahead and work out, in principle, work out exactly how the exciton energy exciton wave function is going to be changed by the coupling to light in the case of very strong light matter coupling. And so we can now make predictions for how this polariton, single polariton even, can change when we couple it to light. And so what we can do, you can actually go ahead and we can even compare it with experiment, because what you can do is you can put the polariton in a magnetic field and use that as a way to probe the light-induced changes to the exciton. So I won't go into details. You can go ahead and solve the same problem now, putting it in a magnetic field. And there's sort of various tricks you can do to solve that problem. But once again, what you can do is then look at how the energy of the polariton, this is what's plotted here, delta E, for a given magnetic field, how the energy changes as, compared to if there was no magnetic field. And you can look at it for both the upper and lower polaritons. And basically, if you plot it as a function of the exciton photon detuning, the difference between excitons and photons energies. In the one case, if it was just, if there was no change in the exciton wave function, and it was the only effect the detuning would be to just change the exciton fraction of your polariton, and so you wouldn't expect, you expect some lines that would eventually cross between you'd expect the upper and lower polaritons to be just have an even relationship. They would, basically what you're seeing here is something that's very different if the exciton was completely unaffected. So you're seeing the way in which they both shift with energies is a clear kind of signature of how the exciton has actually a different size if it's in the lower polariton. So it shrinks when it's in the lower polariton, and it gains in size, it actually expands when it's in the upper polariton, just due to the interactions with light. Okay. And finally, since I think I've only got got a few more minutes left here. So finally, I just wanted to mention one last thing, which is coming back to interactions in this regime. So the measurement of interactions. So previously I was talking about interactions in the case where the exciton binding energy is much larger than any other scale. And now if we're in a regime where the exciton binding energy is comparable to light matter interactions, which is basically was the regime of this experiment I flashed previously of this AMU experiment. Now, and that corresponds to these sort of black dots here. So the question is, okay, what can we conclude from these? Can we say anything more about these kind of experiments? Now that we know, now we're sort of beyond the regime of our other theory, but we know now we'd expect it to approach at least the Born approximation. So now the lowest line here, let me explain. So the low line here is what we'd calculate if we had just the same expression I just calculated before, two-dimensional excitons, I calculated the Born approximation. And so I find a line that's lower than what actually they find here, which is a bit puzzling because, as I mentioned before, I would have thought this would be an upper bound on the interaction strength. So, and also we know we've checked and there are no, at least the polariton energy is much, much lower than any kind of Biaxaton energy. So we'd expect this, we're looking at essentially the ground state of our system. So this should hold. So, okay, so what are we left with? Well, one other possibility, so if we worried about the fact that these excitons in these kind of quantum wells are not strictly 2D, they have a sort of, they have a kind of component in the Z direction, the third direction. If we try to sort of estimate what that would be in that case, then you find, so this is like using a three-dimensional exciton wave function. You find another curve that sits above. So what this suggests, at least, is that in this case, at least for these quantum wells where you have sort of a more 3D-like exciton confined to this 2D kind of plane, that this is having an effect also on the kind of interactions you have in these systems. Okay, so to sum up then, you have, okay, we can see how the exciton wave function changes with a strong light matter coupling. And we can also see how the interactions also appear to approach this Born approximation in this regime, although once one actually accounts for the fact that maybe the excitons are also kind of affected by the fact that they're not strictly 2D. Okay, so then to conclude then, so what I've argued here is that there are certain situations counterintuitively, where the coupling to light can enhance interactions in matter, even though light itself, photons don't interact by themselves, they can actually enhance the interactions. And this also extends to other situations, like if you're looking at polariton-electron interactions, for instance. So we've also looked at that problem, which I haven't had a time to talk about today. We've sort of obtained some analytic results for the case where you have a large exciton binding energy, so we can extract some expressions in that case. And we're finding that the Biaxaton bound state, so the bound state of two excitons, can really strongly affect the interactions of polaritons in 2D materials. And we're able to also work out in the sort of other regime where you have very strong light matter coupling compared to the exciton binding energy, we at least know how it behaves for the case of a single polariton and how the exciton wave function is changed in that case. So interesting outlook might be to ask or at least delve into more detail what's the role of dark states in this problem. And there's even is there the prospect of maybe even using some of these ideas to tune the interactions between polaritons? Although I know these are complicated systems, and we probably have to think long and hard about how to actually use these ideas. Okay, so anyway, so I'd just like to acknowledge my collaborators and group members. So a lot of this work was done with my collaborator and colleague Jesper Levinson and my postdoc Olivier Bleu and former student Emma Laird and colleague Dimitri Efimkin, and also former postdoc Leo Lee at Monash, and also my collaborator Francesca Marchetti in Madrid and Elena Ostrovska, who runs the experiment at AME. Okay, so thanks for your attention.
Thanks, Meera. That was really interesting talk. I think there's one Q&A, one question queued up in the Q&A from Zimin Lee. Thanks for an interesting talk. Is there any difference or similarity between the very strong coupling in your talk and the ultra strong coupling between light and matter?
Okay. Yes. No, that's an interesting question, actually. So, yeah. So I guess in our case, we always were assuming that we could apply the rotating wave approximation, and so we were always assuming that that the frequency of our photons, or at least the scales of the photons, or the energy scales we're probing, were always smaller than the band gap energy. So in that sense, we were never really close to the ultra strong coupling limit. We were just assuming that the actual matter quasi-particle interacting with that could be strongly changed by the light. But it's an interesting question, actually, how what are the similarities? I mean, I guess in the sense that so I'd say the big difference, of course, is we don't have, I mean, the rotating wave approximation holds in our case. So that would be a difference. Perhaps a similarity, I guess, okay, this is only something which just started thinking about, is perhaps maybe in the way in which they modify the matter parts. I mean, that's something that certainly I'd be interested to explore further, like is there anything in which, anything in the way that exciton is modified, whether that has any analogy in the ultra strong coupling case. I don't know, actually, that's an interesting question.
The graphs that you showed when you were looking at the energy landscape in K-space effectively always showed the energy of the upper and lower excitons. Polaritons are separated. Is it ever possible to get degeneracies there?
Okay, yes. No, that's another good question. Hang on, let's find a picture. Oh, okay, anyway, maybe or maybe not. Yeah, so I think that comes back to, okay, let's say we have this picture. Yeah, so I think that'll come back to then, I think maybe what you're asking is, it's probably related to how strong coupling we are, in the sense that, can I ever lose strong coupling as well? Like, there can be regimes, I think, where, people see that when they start pumping it harder and harder, they start to lose the gap between the upper and lower polaritons, and essentially, even start to lose polaritons. They lose and I think it's related, I think, to a number of things. I mean, this is still something that's being looked into, but whether there are other sort of incoherent processes that dominate over the coherent kind of coupling between excitons and photons. I don't know if this answers your question, but
yeah, it does. Yeah.
Yeah.
What I was thinking specifically about also was, therefore, it's not possible then, for example, to get like any direct cones in this energy landscape.
Oh, okay. I think people have been playing around with. Okay, I think people have been doing some interesting stuff with the spin degree of freedom, if I remember correctly, and also putting like polaritons on lattices. So I think people have managed to construct some very kind of interesting sort of band structures and dispersions with polaritons in that case, from what I understand.
I was thinking about one of the last graphs you showed, where you showed the effect of probing the system with external magnetic fields, as to whether or not you could induce degeneracies that way, and in particular, if there would be any associated Berry phase as you moved around that landscape. That was.
Yeah. No. Actually. Yeah. No. That's interesting. I think. Yes. I know. People, like I said, I think people have been thinking a lot about this in the case of, these sort of engineered or artificial lattices for polaritons, and also making use of the spin degree of freedom to introduce precisely these effects like Berry phases and so forth. With the magnetic field, so we were, we were just finding, actually, if anything, they were lifting, well, at least even, sort of opening up gaps rather than increasing energies.
You were going the wrong way. Okay.
Yeah. Yes.
I guess a kind of semi-related question. You never get a situation from an experimental point of view. I guess you can't get a system where the coupling to the vacuum is so strong that becomes important for the physics.
Oh, okay, I see. So probably this comes back to maybe if you're in the ultra strong coupling limit, I suppose. Yes, I mean, so in my case, in our case, I think because I have such a large band gap, what I'm looking at least, it will not be affected by that, is my feeling. But certainly, if I'm going into an ultra strong coupling regime, then I agree. Then you probably need to worry about these kind of effects. Yeah.
No, it's really interesting. I mean, it's a fascinating area. That's Sure. I don't see any other questions. So let me thank you once again, Meera, for a really fascinating talk. I'll remind everyone that Meera's talk will be available on the AOP YouTube channel within a couple of days. I'll certainly be watching it again. Oh, there's another question that just popped up, I think. Oh, Ross wants to know the role of thickness. I guess he means the role of, well, you did mention briefly
right.
in the limit of monolayer of atoms.
Yes. So are you asking about the role of thickness in the interactions or in general, or?
I'm not sure. He just said wrong.
I mean, well, yeah, actually, what we were finding at least is that, okay, so certainly if we're looking at atomically thin materials, then they're effectively, really 2D, we don't need to worry so much. I mean, okay, we don't need to really worry about the third dimension.
Except perhaps that the atoms can be momentarily displaced from their equilibrium positions.
Yeah, I guess that's, yes. Although I suppose that's at such a high energy scale. I mean, there are some screening effects. Thick material. Move towards 3D. Yeah, so that's an interesting question about like how it affects the interactions. It seemed like the interactions, if we believe, like when we're comparing with theory experiment, it seemed like the interactions were more affected by the thickness than the actual, like the exciton, how the exciton was being affected by light. Like when we were looking, so we had a 2D theory which we could happily compare with experiment and look at, and it didn't seem to matter what the thickness was. I mean, okay, that's of course when assuming we're in quasi 2D. But yeah, as you get to thicker and thicker ones, that my guess is at least we're finding the interactions change first. And surface wave, can we get surface waves on each surface? Okay, that's an interesting question. Something I haven't looked into.
And that interesting counterintuitive result that you got, that the polariton binding can be stronger than the exciton.
Yes.
Binding. What was it? I think I thought about something else and I wasn't concentrating on the slide.
Oh yeah, no worries.
What was determining the maximum binding energy there on that graph?
Oh, yes. Okay, no, that's sorry, I don't know if I should. I know probably.
It's probably just the equation on the screen, but I didn't digest it all.
It was, I think you were asking about this.
Yeah.
This one here. Yes, no, actually, I sort of skipped over that, but actually, yes, no, you're right. There's an interesting feature here, and what's behind that is it's an interplay actually between how the exciton fraction is changing as you change the momentum. So how it's becoming, it's trying to become more excitonic as you go towards the exciton, the high momentum, the exciton line here.
Right.
But at the same time, you're still benefiting from this shift in the energy that you get from the light matter coupling from being in the polariton state. So what this does then is you end up with having this. So eventually, you'll go back down to the exciton case.
Yeah.
But there's this kind of sweet spot in between where you've reduced the exciton fraction, but you've still got a large shift in the energy due to the light matter coupling. So that gives rise to this peak here, if that makes sense, of the interaction strength.
I see.
Yeah.
But there's still a difference then for K equals 0.
Yes. Yeah. So actually, yeah, we're finding that it starts to increase a lot away from K equals 0 as well. Yeah. Yeah. There's still a difference at K equals 0. Yes, that's right.
So Ross wanted an extension to his question. He wanted to know if you can get surface waves.
Yes, I saw that one.
Yeah.
That's something I haven't looked into. It sounds interesting though. Yeah.
Fascinating. Well, thanks very much, Meera. Thanks everyone for attending. We'll keep everyone informed as to when the next talk is happening. And thank you all.
Yeah, thank you.
Bye for now.